In this session, I would like to talk about ALU and data path. So far, we assume that whenever we have instructions, they are automatically getting executed, correct? But that is not true. Someone should execute them, correct? Now, how that execution takes place, we are going to study now. So that is a topic called ALU and data path. First, we study that. After that, we will see a concept called pipelining. Pipelining is also very important topic for us. So in pipelining, what are we going to study is how to execute the instructions parallelly. Before that, you should know how a typical instruction is going to be executed. For that, what is the machinery we have, how to arrange that machinery, that we will study in this ALU and data path. Okay, so after that we will see how this pipelining effectively work and how effectively that pipelining is helping us in executing the instructions parallelly. We will see that later. First of all, you should know how to execute an instruction, what are the various phases we have, everything. Okay, let us begin with typical steps in instruction execution. So you might think that whenever instruction is getting executed, so this idea, right? So first of all, we have to fetch that instruction. Yes, after that we have to execute. Absolutely right. First of all, we have to fetch it, after that execute. So if I extend that idea, whatever you told, fetch and execute, then I can understand the same idea with three steps. You see, typical steps in instruction execution is, first of all, fetch the contents, correct? So I assume that, let's say, your instructions are already loaded in main memory. Okay, let me store them here: I1, I2, I3, I4. Okay, now initial starting address is 100. Now there is a register called program counter. That program counter is already stored with 100. Let's say that is the assumption. Your assembler, otherwise loader, sorry, not assembler. So loader, once you have a machine instruction program, then the loader can do this thing. That means your program can be loaded somewhere in the memory and the starting address can be kept in program counter. Such a way loader will work, and after that your program starts executing. Okay, now I'm talking about this idea. When you have already your program in your memory and program counter already showing the starting address, that will be done by loader. Now we will not worry about that loader part. We will see now the remaining part. Once you have this configuration, what are the things are going to happen, we will see. The first thing is, fetch the contents of the memory location pointed by program counter. Correct. That means program counter points some instruction, fetch it. So fetching is nothing but you have another register called instruction register. Remember it. Okay, so your machinery should be designed such a way that, so that instruction which is pointed by this program counter should be transferred to instruction register. Okay, then I1 will come. So that is nothing but a memory operation. Okay, we can design, not a big deal. Okay, so it is just transferring the data from 100 to this instruction register. So that is what the first step I can say. Now using register transfer logic, so otherwise in high level, symbolically I can show like this. The content of IR should become what? You see, content of program counter, we have to go take the content of program counter. This content of program counter is 100, correct? Then content of 100, that means value at 100. What is value of 100? I1. So I1 should be fetched into instruction register. So that is the first step. Now one more thing. The students who are watching my lecture, if you want to understand pipelining very clearly, first you should understand how your instructions are going to be executed. Then only we can clearly understand pipelining. That's why we will go very slow first. Second step is, increment the program counter to point the next instruction. That's obvious, right? Once we execute this instruction, what are we going to do? We are going to execute the next instruction, most probably, unless it is a branch instruction. I'm talking about regular thing. Okay, now if it is a straight line program, that means instruction execution is in a straight line sequencing, then what is going to happen after this step? Program counter will be incremented by 4 units, because I am assuming that every instruction consumes 4 bytes. Okay, that is one thing. Every instruction consumes 4 bytes. Second thing, I am assuming this machine is byte addressable, so that the next instruction's address will be 104. That's why PC equal to PC plus 4. So here this suffix, if I write like this in the braces, like the meaning of that is content of PC. Content of PC is what? 100. 100 plus 4, 104. 104 will be stored in PC. That is the meaning of this one. You can easily understand. What is the third step? Carry out the operation which is specified by the instruction in instruction register. That's it. Already we faced the instruction, right? That is where in the instruction register you execute it. But still you did not teach us how that instruction will be executed. I will explain that part. But if you see in the broad way, there will be three things, correct? Fetch the instruction, increment the program counter. Third step is carry out the operation. This is general thing, right? Unless there is a branching everything. We will see that things later. So this is a rough idea. Now, sir, what is the meaning of execution generally? So whenever I say we are executing the instruction, most probably in RISC instructions, we will be doing these things, I will tell you. Example, let's say one typical instruction is load, correct? Focus on these three instructions first. Load, add, store, okay? In load, what are you going to do? If really, let me write load first. Load into register R1, something memory of 1000, okay? Something memory locations 1000, okay? That means what? The value at memory of 1000 we are storing in R1, correct? So second thing, let's write like this, add R1, R2, R3. That means what? How to execute this one? Really, if it is executed, what is going to happen? R2, R3 will be added and that result will be stored in R1, remember it. Similarly, store can be understood like this. Store R1, we will be writing something memory of 1000. This time, we will be storing some data which is now in R1 into memory of 1000. Of course, you know that, right? So, in these three instructions, if you observe, the one thing you are doing is you are accessing the memory, correct? In this instruction, you are accessing the memory and getting some data and we are storing into R1, correct? That means transferring the data to R1. Second thing here, you are adding the values which are stored in R2 and R3. That is what you are doing here. Now after that you are storing the result into R1. Now what are you doing here in store? We are storing the value which is specified in R1 into a memory location 1000, correct? For that we are going to memory and we will be storing the result. So if you understand these three steps, then you can understand this one. What is that? The major steps in execution of any instruction, typically this thing. You will be doing these four operations. See, the major steps we perform generally is reading the contents of a given memory location, correct? You see, example, if I write, the meaning of this one is load R1, let's say memory of 1000. To execute, whenever you are executing this instruction, what are you going to do? We are going to, take the value from the memory location 1000 and we are transferring into R1, of course. For that, we are reading the contents of a given memory location, correct? Maybe you are doing that. I am not saying that always you do that. It depends on the instruction. Otherwise, you will be doing, reading the data from one or more processor registers. Example, let's say you are doing addition. Add R1, R2, R3. Then what are you going to do here in this one? Execution means read the value in R2, read the value in R3 first, after that do the addition, correct? So maybe you are reading one of the typical operation you will be performing in add R1, R2, R3 is reading the values in the register R2, register R3, correct? So that is one typical operation you will be doing, correct? Without that, can you do that? No. So that's why. Third thing, perform the arithmetic or logic operations in C. In this one you can see. After reading, example, you see this one, add R1, R2, R3. Whenever you have this kind of instruction, what might happen is, so your register R2, register R3, that data will be first of all read somewhere, okay? So we read this value. Mr. Read R2, please give your value to me. Mr. R3, I am taking your value into some temporary register temp1, temp2, let's say. That means what? We are reading the data in R2 and R3. After that, we will be connecting them to maybe adder, correct? Adder circuit. If this happens, then what are we doing here? To do addition of R1, R2, R3, we are reading the data from R2 and R3. Then we will be adding them later, correct? So that's why I can say that. So typically, the typical instructions typical operations we use in execution of any instruction, maybe reading the contents of the memory location or reading the data from one or more processor registers, otherwise performing the arithmetic Arithmetic includes addition, subtractions, multiplication, division, maybe left shift, right shift, everything. Otherwise, you will be busy storing the data into memory locations or registers, correct? Store data from processor register to a given memory location. Maybe you are storing the data from processor register to given memory location. These are the typical operations we are going to do whenever we execute an instruction. That is about instruction execution. Now we will see more details. See, slowly we started understanding what is instruction, correct? After that we understand typical steps in instruction execution. After that we realize that what are the, execution of instruction means what are you doing? Maybe you are adding, maybe you are reading the registers, otherwise you are reading the memory location, otherwise you are storing some value into memory, right? These are the typical operations we perform, especially in RISC kind of instruction set, correct? Now we will see more details, okay? Now we will see hardware components related to this instruction execution. Whenever you are executing instruction, then what are the things you require? One is register file, correct? That means set of registers, CPU registers, you know, right? Maybe 32, 64, whatever. Now control circuit. So this is very important. This control circuit is going to generate signals appropriately so that at appropriate time right action will be performed. We will see that how this control circuit can be designed. That is the major goal of this this chapter, I can say. Now instruction register, because whenever you have a instruction that is initially in memory, right, then we have to fetch that into instruction register. Remember one thing, always we are bringing that instruction into instruction register and we are going to process. That means how do you know that we have to do addition or subtraction, otherwise load? For that we have to decode it. So that decoding and everything will take place after keeping the instruction into instruction register. So once you keep your instruction in instruction register, this control circuit is going to process it. We will see that. Now register file is done, control circuit is done, instruction register is done. So what is ALU? Why we require ALU? You know that, right? So we'll be doing addition, subtraction, multiplication, divisions, right? Left shift, right shift, arithmetic shift, everything. For every such operation is performed using some circuitry. So that entire unit let us call ALU, okay? Arithmetic logic unit. Now instruction address generator. So instruction address generator is a big circuit. So we will talk about this one now. So why it is required? Example, when you have started executing your program, then maybe first instruction, after that we have to go to second, after that third, right? Sometimes what happens, because of the logic in the program, because of the some special instruction like jump instruction, otherwise function call, we have to change the program counter value to something else rather than linear, correct? So generally when your instruction starts at 100, let's say after that 104, then we execute 108th instruction, after that instruction at 112, so on. Suddenly we go to 500 because of so many things. One is maybe it's a function call, right? Otherwise if there is a branch instruction, right, already we have discussed that because of branch instruction, then we will go to some other part of the control, otherwise some other part of the instructions. For that, finally this program counter is going to be modified, okay? Initially let's say program counter is having 120, then because of the instruction, maybe you might have this kind of instruction, branch to an instruction 200. See this instruction, branch to 200. That means so whenever this instruction is executed, then this 120 should be changed to 200. Who will do that? Correct? There should be circuit. So that is nothing but instruction address generator. So finally the story is all about executing the instructions one by one, but where is the next instruction? Maybe sometimes when you are at 120, the next instruction might be at 124 or 200. That is decided by the pure logic of the program. So that's why instruction address generator is going to understand the instructions, current instructions, and it is going to change the program counter appropriately. So we will see that part, like how instruction address generator is going to consider various possible addressings, okay? Now the last one, processor memory interface. If you see, we have load instruction, store instruction, add, everything. So we have, sometimes we have to visit the memory, correct? So whenever you want to visit the memory, then there should be some circuitry, that is processor memory interface. How this can be understood, I will tell you. So you have a memory, okay? So there is a person, for him, so you are here now. This is the memory. Okay, I am talking about this person. Let's say call him Raju. Now, example, let's say you have some address called 200 in program counter. Now, just simply give that 200 to Raju. Raju, I am giving you an address. I want content of the 200. Okay. So, Raju is going to, Raju is going to that appropriate memory location 200 and he will fetch the data and he will give that data in some other register. Okay. Let us call it as data register. Okay. Now, what are you doing? You are providing some address in some address register. Okay. Let's say, and we are communicating with Raju. Raju, take this address and give the data. So this is the data register in which you have to keep the data. That's it. I will be very happy if you do that. For that, Raju, what Raju is going to do? He is going to that memory and he is fetching the data, correct? So for that, it's just, you are understanding it like a person, right? But it is not, actually he is not person. There should be a circuitry, correct? So that circuit should take care of all such things. What are the things? Given address, he should fetch the data. Second one, given, sometimes I give address and data like this. 5000 is the data. Then I call this Raju and say, Raju, this is the address 200. Go there and write this 5000. Then he should go to 200 and he should write 5000. Such a circuit I want, right? Sometimes it is needed, right? Majority of the instruction execution is nothing but doing this stuff. That's why we have a separate circuitry that is called processor memory interface. Finally, these are the essential things. CPU registers required, control circuit required, and ALU and instruction register, instruction address generator, and processor memory interface. So using these, only these, I can say hardware, we will be executing our instructions. We will see more details of how an instruction can be executed. Okay. Now, before that, I would like to tell you one thing. Whatever may be the circuitry, this is the major circuitry, right? Now, question number 1 is how to design it. That means finally what is our goal? We have instruction that should be executed. So that instruction execution can be divided into, that means how to understand that instruction execution is, we can divide that into some operations, right? Correct? So every instruction execution can be seen as doing some small operations, okay? Operations. We will be seeing that operations one by one. Okay. Example, in addition, what are the operations? Fetch the instruction. I am talking about add instruction. Fetch the instruction. Once you fetch the instruction, next you have to understand that decoding. Then third operation is what? Execution, right? So all that operations we are going to do with this circuitry. Okay, we will see that. But the design part I am talking about now, we can design that in two ways. One is, multi-stage, single stage. So finally you realize that to execute your instruction, you need some machinery. That machinery can be designed into two ways. One is single stage, second one multi-stages. Okay. Sir, why multi-stages are required? I will tell you. First of all, we'll focus on single stage machinery. Now we'll see one example and we talk about this machinery properties. Okay. Example, you have a instruction load R1 comma something 5000. When you have this kind of instruction, to execute it, we can design the circuitry in two ways. One is single stage, second one multi-stage. Let us talk about pros and cons of the single stage and multi-stage machines. Okay. So in single stage machine, what is going to happen is you will be having a circuit that is going to take your instruction I1. Let's say, let us call it as I1. Okay. When you give that I1 to this machine instruction, otherwise circuit, sorry, then what is going to happen is the desired task, we know what is desired task, right? That desired task is going to be performed. Okay, desired task in one single stage. That means for that we directly give the input and you get the output. So I don't know how many clock cycles it requires, maybe 2 clock cycles or 1 clock cycle. Maybe you can do it in 1 clock cycle. Sir, how can you do this much big task in 1 clock cycle? Yes, we can do. Simple, because we can extend the length of the clock cycle. Example, let's say the duration of clock is 1 microsecond, just for time being, assumption. Okay, so if within 1 microsecond, if this circuit won't stabilize, that means this circuit cannot compute all the things which are required in this operation or instruction, then what we do is we take a bigger clock. That's it. Take a big clock like this, 2 microsecond. Fix the clock to 2 microsecond. If it is not sufficient, go to 3 microsecond. That's it. In that way, so we can design a circuit which can execute this instruction in one clock cycle. Okay, so that is single stage machine. Now we can have another concept called multi-stage machine. So multi-stage circuit. In multi-stage circuit, what are we going to do is we are going to execute this instruction in multiple phases. Okay, so let us take one case called 3-stage machine. Okay, in 3-stage machine, what we are going to do is, this is stage 1, this is stage 2, this is stage 3. Okay, now you have lot of registers. I will tell you, this is called register. Why we require registers in between stages, I am going to explain you. So this is called multi-stage circuit. So I am dividing the work of that instruction execute into some parts. Okay, so finally executing this instruction, first of all we have to fetch it, right? So I do fetching here, maybe, then I decode here and I execute. In that way I divide the work into 3 parts. So here maybe, so here some input will be given, right, in this register. To fetch the instruction, what you require? Program counter. Maybe the program counter is stored in this register. Try to understand in high level, don't go into details. So slowly we will try to understand it. Okay, now these registers are going to be used to store the information which is required to fetch operation. Before fetching, what you want? Address of the instruction, that will be provided in this register. Okay, now fetch it. Once you fetch it, that instruction will be, so here I am doing decoding, right? To do decoding, Mr. Decode, what do you need? I want instruction. Okay, so this fetch is fetching the instruction, right? So here once that instruction is fetched, that will be, let's call it as I1. That instruction will be temporarily stored in this register, so that can be used as input to the decode circuit. Correct? Now that instruction, which one, I1, is taken as input by decode circuit, and that is going to provide some output. What is that output? That output, that's a separate story. What is the output of decode is understanding the instruction, that it is load, right, and issuing different kind of control signals. We will see that. So far we don't know like how to generate the control signals, everything. Finally the goal of decoding is nothing but understanding the operation. Okay, now once it understands the operation, it will see that, because since it is load, right, so for loading what you require? Maybe memory address. We have to go for memory address, right? So that's why, so next phase is execution. This decode step will gather all the information which is required for execution phase and it will supply. Maybe execution phase require memory address 5000, because this execution phase should go to memory. That's why, where to go in memory? 5000. That will be supplied by decoding. Okay, in that way these stages are going to help each other, right? Stage 1 helps stage 2, stage 2 helps stage 3 through the buffers. Okay, in that way, so these buffers are going to help in forwarding the data to the next stages, right? So that is what the idea of multi-stage circuit. But sir, why we have to do the things in multi-stages? I will tell you, there is a concept called pipelining. So in pipelining, whenever your operations, otherwise it's a task or work, this is instruction. Executing instruction is a work. Okay, so whenever the work is distributed into multiple stages, then pipelining is going to give us an advantage. Then we can have parallel execution. That's why we will be studying pipelining in very detail. At this moment you remember one thing: whenever you have some work, that means here executing the instruction, if I can divide that into some stages or some distributed works like this, that means if I divide the work into multiple parts, then we are going to get the benefit in pipelining. That's why we will be converting it into multi-stage problem. Okay, now while designing the circuit itself, we will be designing it such a way that circuitry will be divided into stages. That is what I would like to say. Rather than single stage. In the single stage, all the circuit will be, you know, messed up, and there will be only one stage, and input will be instruction, output will be the, what is the output? Executing that, correct? But in multi-stage, we divide the work into systematically into multiple parts, and we'll see one by one. We'll do one by one. Okay. So in real life, we have such kind of things. Example, let's say some people, like, you know, car manufacturing. While manufacturing the car, you know, the work will be actually divided into multiple parts. Okay. Someone creates engine, someone will design. Remember one thing. Example, you want to create a new car. Designer will be someone like, you know, the engineer, correct, who is going to design the car model, everything, right? Now second part, manufacturing will be different. Some other people will do the manufacturing, right? So in that way, maybe coloring, who will do the painting? Engineer? No, correct. Who will do that? Some other specialist. In that way, we divide, or creating the car is divided into multiple parts, correct? So for everything there can be a specialist, rather than, you know, imagine this one. Let's say you are creating a car, or you are designing a car. Finally, you want to have a end-to-end functionality. That means you want to create a new car. Then first we have to design it. Then after that we have to, you know, assemble it, right? We have to create all the parts. Then after that we have to assemble it. Then we have to paint it. Correct. We have to advertise it. If you do everything, then definitely, is it not awkward? Yes. At least, you know, advertising part definitely cannot be done by engineers, right? That's why some management people should be there. In that way, so always if you divide the work into multiple parts, then you get benefits, right? Similarly here also, so that we will be seeing in pipelining, we will be getting the benefits. That's why the functionality we will be dividing into, you know, stages. We will see that stages, how many stages are required. If you want to ask, then ask me. That, you know, the answer is very simple. The number of stages depends on the experience. Like, you know, we will see that. For that you should understand the instructions carefully. What I do is I show you all different instructions, and we'll try to understand what is the meaning of each and every instruction. To execute that instruction, what we have to do. Then after that we'll come to number of stages. Okay, we'll identify that. Let's postpone the number of stages problem now. Now we are going to understand first of all each and every type of instruction, like load, store, add, everything. And we'll be closely observing what are the things are going to happen in that instructions. Okay. Now to understand how many stages we require, okay, in the circuit, first we try to understand load instruction. Like, you know, what are the operations, small operations we have in, okay, that load instruction. If you see load instruction, example, load R5 X of R7. I'm using indexed addressing mode. Okay. So in index addressing mode, what are we going to do? How to understand this instruction? We first of all forget about that time, you know, how to do it. First of all, the very important step is we have to fetch the instruction, isn't it? So that is clear. Fetch the instruction. After that, understand it, correct? Before that, increment the program counter, correct? Because once this is done, maybe if it is, you know, not a branch instruction, otherwise not a function call, the next instruction to be executed is definitely after this one, right? That's why increment the program counter is the second step. Let us do that. Fine. Then the third step, understanding it, you see. Decode the instruction to determine the operation. Yes, we decode it. Then fourth step, add the immediate value X to the contents of R7. We know the execution model, right? So what we are going to do is in this load R5 X of R7, X plus R7 will be computed, correct? That means the content of R7 is added to X. Then you get some value. So we will be going to that memory address. Example, R7's content is 100. Then X is, let's say, 200. 200 plus 100, 300. Go to memory address 300 and fetch the data. That means fetch the data and store it in R5. That is what the operation, right? So I can systematically write like this. Not a big deal, right? So third step is understood. Fourth step is add the immediate value. This is immediate value, right? X. Correct? That immediate value we have to add to content of R7. Why we say immediate? Because so in the instruction itself this value is represented, but 100 is not represented in instruction. What is represented in instruction? Register address, R7's address. Then we have to go to that address, then we will get content. That's why I can say that X is immediate but not R7, right? Now So that's why add the immediate value x to the contents of R7. We know that the fifth step is use the sum x plus R7. Yes, I use that as the effective address. Yes, now 300 is the effective address for what? Operand. Address of the source operand and read the contents of that operand. Yes, I do that. Then last step is what? Once you read that operand, you store it in R5, right? Load the data received from the memory into the destination register R5. So there are 6 operations. Now these 6 operations, if you closely observe, we can write them into 5 major parts. You see them, okay? Sir, how do you know that we can write them into 5 parts, not 4 parts or 3 parts? It comes by experience, okay? So already that architecture people who are experienced, okay, so since hundreds of years they are creating new systems, and they realize that, so especially for this kind of risk kind of instructions, the best way of designing is 5 parts. Just understand it, like example, let's say really I'm dividing this entire work into 5 parts. How it looks like we will see, okay? Slowly you will realize that, and you will be convinced that it is really good to design our operations. Otherwise the all operations of this load instruction into 5 parts. Why? When will you realize it is after learning store operation and add operation, everything. First of all, just understand what are that 5 operations. Again, one more time, okay? First step is fetch the instruction, correct? We do that. Here also we did the same thing. Then increment the program counter. So that means 1 and 2 are merged in one way, okay? So finally, in one step you do this one, fetching the instruction and incrementing the program counter. In the second step, what you do is decode the instruction and read the contents of register R7 in the register file, okay? See here, what are we doing here? Decode the instruction and understand it. At the same time, read the contents of R7. That we can do in second step. Now, third step, you see. In the third step, compute the effective address. How to compute the effective address? Recall, example, already you read the value which is in R7, which is 100. Now, I want to compute the effective address. What to do? Already this X value is available with instruction itself, correct? Because whenever instruction is given, where we are storing it? When you fetch the instruction, we will be fetching it into instruction register, right? So in the instruction register already we have X value 200. Now take this 200 and take this 100 and add them. Then you get effective address. For that, here we have to use adder circuit. In the third step, we will be using adder circuit. Sir, where is the circuit? We will see that circuitry part later. First we understand how to divide the entire work into 5 steps, okay? So compute the effective address. Yes, using the arithmetic logic unit, we can do it. If you observe one thing, so far we have not at all used any addition subtractions, right? So in the third step we are doing arithmetic, remember it. So in the first step we are fetching. In the second step we are understanding the instruction, and at the same time we are reading the data from register 7. Now fourth step, read the memory source operands. Okay, read the memory source operand. That means we will be storing, did you remember? Let me write the instruction here. Load R5 X of R7. Finally, we have to get the data and we have to store it in R5, correct? Now after third step, what is it available? Address is available, right? Where to go? Now in the fourth step, go to the memory and prepare the source operand. That means get the data from that. So read the memory to get the source operand. Yes, I do that. In the fifth step, what we do is, load the operand into destination register R5. Correct? Because already we got the data. Now we will be storing it into R5. In that way, we can imagine our instructions execution into 5 parts. Here execution means from scratch. Fetch it, decode it, do the remaining things, execute. So execution we are doing into 3 parts, right? Into 3 steps. So this entire thing is, I can say, a 5-stage design, correct? Or 5-stage design. So, sir, why are you using 5 stages? Still we are not convinced. You will be convinced only if you understand other instructions. Now similarly we will observe the next instruction, which is add instruction. Okay. Now we will see add instruction. After that store instruction, and slowly you realize that there is a similarity between add instruction, store instruction and load instruction. Okay, the operations in this add, store and load are almost same, like they have some I can say uniformity. We will see that. Example, let's say add R3, R4, R5. Okay. So here you tell me what are we going to do. First of all, we fetch the instruction. When you have load instruction, what did we do? We fetch the instruction, right? So that's why step 1 is common. We fetch the instruction and increment the program counter, correct? So there is a same model, that's why. So remember one thing, the major principle of RISC is like this. When the instructions are similar, the design will be simple. The circuit to execute that instructions will be simpler. Okay, that's why. So RISC instructions are like almost they are all having the same functionality. Okay, same operations. Now we will see. First step is same. Second one, decode the instruction. Yes, that is common to everything. And read the contents of source registers R4, R5. Here we have to read R4, R5 their contents. Okay. Same thing, like just compare with load. There also we did the same kind of stuff. The third step, in the third step we did computation, right? That means we did addition. Here also compute the sum which is already read here. R4 value, R5 value we read into some registers, then take that R4 and R5, connect to the adder. That's it. In this third step you connect it to adder. That means already we have adder, correct? Now we are using it in the third step, correct? Now adder contains two inputs, and let's say assume that adder is already connected with some registers like this. Now the only thing is, if you say my dear adder, please add, automatically it will add. The only thing we have to supply the data. So the supply of data is done at second step. You see, decode the instruction and read the contents of source registers R4, R5. So the contents of R4, R5 might be read here like this. Okay. Now R4 will be read here and R5 data will be read here. Then the third step will be just computation. Now after that, fourth step, you see the fourth step. Load the result into, you get the result right here, let's say. Already we have result now after third step. So that result we have to load into destination register R3. Obvious, right? Now we have to take this data and we have to go to, already I told you that we have a register file, correct? Register file. In register file, so there will be a register called R3. And sir, where is the address of R3? Instruction already contains address of R3. So now go there and simply write the data, correct? That is what the meaning of this one. Load the result into destination register R3. Already we have address of R3. Simply enable that register and write the data. That will be done in step number 4. Sir, what about step number 5? Already operation is done, right? I mean, everything is done, nothing to do. So in the step 5 we can keep quiet, correct? But what we do is, rather than keeping quiet here, we keep quiet in fourth step. I will tell you the reason. In the load instruction, if you recall, what we did, let's say load R1 something. Then in the last step, we loaded the value into R1, correct? So here also, if I do the same thing, then you are going to get benefit. That we will be studying in pipelining. So that's why design should be same. So here you do the fifth step rather than fourth step. So keep quiet, fourth step. So in the fifth step, what you do is load the sum into register R3, so that this instruction will be similar to load instruction. Okay. Now when you have similar instructions, then we are going to get a benefit of multi-stage idea, which is in pipelining. Okay. Now we will see the next instruction, store instruction. Before that, I will tell you one more thing. Add R3 R4 hash 1000. What is this? Recall. Add instruction, correct? What is the difference between R3 R4 R5 and R3 R4 hash 1000? This is immediate addressing mode, correct? That means here we have to add R4 and directly value 1000, correct? But in this one, we are going to R4 and R5 and we are reading two registers here. We are only reading one register and another operand is direct, correct? So, I mean immediate for that. So there is no much difference, I want to tell you. So fetch the instruction, same. Then decode the instruction and read the contents of source register R4. Only read R4, correct? Next, compute the sum R4 plus 1000. Then fourth step, keep quiet. Now fifth step, load the sum into register R3, correct? So that's why there is no difference between add R3 R4 hash 1000 and add R3 R4 R5. So that is what the idea in RISC instructions. Almost all the instructions are quite similar. Such a way they carefully planned it. Now we will see store instructions. If you see store instruction, store R6 x of R8. Now x is directly supplied here, example it is 100, then what are we going to do is, we are going to read register R8, assume that its content is 200, R8's content is 200, then the 200 and 100 will be added, 300. So we will be storing the data which is in R6 into a memory address 300, correct? Now we will try to understand it into 5-stage problem. First step, fetch the instruction. It is like load and add, fetch the instruction and increment the program counter. Second step, decode the instruction and read registers R6 and R8. Same thing, there also in add also we have decoded the instruction and we read register R4, R5. Here we are reading R6 and R8, correct? So it is quite similar to add instruction, correct? Now third step, compute the effective address x plus R8. We know how to compute it, correct? So this is the third step, which is exactly equivalent to load instruction step and exactly equivalent to add instructions third step, right? That's fine. So fourth one, now store the contents of register R6 into memory location x plus R8. In the fourth step, what we are doing is, we are storing the contents of register R6 into memory location x plus R8. Already we have this address, let's say 300. Now we are storing the contents of this register R6. Already we have R6 in the instruction. Take that R6 and take the data and directly store into memory. That we can do in the fourth step. Fifth step, nothing to do. Then keep quiet. So in that way, so store instruction can be understandable in 5 stages, correct? Now finally we have seen load and add and store, correct? Load contains 5 steps. But add contains only 4, store also contains only 4 steps, but that 4 steps are quite similar to that 4 steps of load and 4 steps of add, right? In that way we have instructions. Now since all the instructions are almost similar, then the circuit design to execute these instructions will be uniform, otherwise simple, okay? That's why we the designers decided to design the instruction set like this, okay? Now we are and especially focusing on RISC instructions, correct? So we are not going to talk about CISC instruction, which is a little bit complex and that is not suitable for pipelining. But our major goal is understanding RISC instructions and understanding the pipelining and getting the foundation for the pipelining topic. That's why, okay? In this topic, what I am going to teach you is how these instructions are generally, otherwise how these instructions are going to be executed. And what is the similarity I already taught you. Now what we are going to do is, now we are going to understand the circuit, right? Sir, please teach us what is the circuit, like how that circuit works, okay? We will see that.